All right, so where's the chalk? So let me just put up some names. So one of these is a collaborator, and the rest is inspiration or competitors, whatever. So some of it is joint with Makoto Matsumoto. And we've been very delinquent. We were writing something many years ago, and nothing's moved in 2 years. That's about the elliptic case. Sort of inspiration came from Bailenson and Levin. So they wrote a paper a long time ago called The Elliptic Polylogarithm. And there's this related work one is Enriquez. Again, all of this stuff here is in the G equals 1 case. So Layla asked me if this is higher genus. And the other one is Brown and Levin. All right, so the question, and I got to tell you, I thought it was a great topic to talk about at this conference, and it may well be, but I figured out it's a challenge to figure out how to explain it to a diverse audience. So if this, I'm just setting myself up, my excuses up for failure. No, it's okay. So question is, how should one generalize, or how should or can one generalize multiple zeta values, polylogs, and mixed Tate motives over spec Z? How can you generalize all of these things to higher genus? So I think of these things as all being in genus 0. So these things are all G equals 0. And there's a central character so let's just ruminate a little bit on this. There's a central character in the G equals 0 is P1 minus 0, 1, and infinity, right? And so we may have to think about, and the question is, what is it?
Why do you think that mixed-Tate motives over Z are genus 0 case?
Well, ask me that question later, because I could try to answer it now, but that's partly where I'm going, right? So, but I think the idea for what you want to do is partly coming from what Bailenson and Levin did. So in the elliptic case, so what is it? So I'll give you two answers. The first one is it's the simplest hyperbolic curve of genus 0 with G equals 0. So hyperbolic curve, maybe I'll just put a little thing here. So again, I'm a topologist, so my excuse for doing things incorrectly. So if I take some compact surface minus some finite set, x1, xn, the Euler characteristic of S prime, so by that I mean this guy here, is equal to 2 minus 2g minus n, right? And it's hyperbolic, S prime is hyperbolic is equivalent to saying the Euler characteristic of S prime is negative, right? And why do we care about that? It's the same thing as saying it has a complete hyperbolic metric and a finite, complete implies finite volume. And the other is that if you put a complex structure on this, then its automorphism group is finite. So, and another way would be to say it's GM minus the identity. And you hear this in both talks. And so I want to say, how would you generalize these? So I would, one, you would think of hyperbolic curves of higher genus. And two would lead you to, say, varieties of higher dimension. So you should think of this somehow as an algebraic group, and you've removed the identity. And one reason you remove the identity is you get an interesting pi1 when you do that. And so this suggests there's two ways to generalize. So this suggests two generalizations. One that where you, and I'll explain what these mean later on, where so higher genus curves and higher dimensional abelian higher dimensional groups, right? And by groups I mean principally polarized abelian varieties. I won't talk too much about this, but I do want to say something, because there is a literature on this that I don't understand. And so, so they intersect. So the intersection, so G equals 1, M11 is the space of elliptic curves is equal to A1. So a genus 1 curve with a genus 1 hyperbolic curve is a genus 1 curve with a point, which is a one-dimensional abelian variety, right? So they agree in genus 1. And so people are already studying this elliptic case. And like I said, I think I'll mainly concentrate on curves, but I think I want to say something about abelian varieties. So a warning. There are many kinds of people in this room. I'm not a formula kind of guy, and but doesn't mean to say I don't like to compute. I can compute things, but they're different from writing down formulas. So what happens in either case here is, let me just say, genus is G here, dimension is equal to G. So if we're talking about abelian varieties, the dimension is G. Warning. Actually, I think I'm. Okay, let me go a little further. Maybe I'm not explaining it the best possible. Okay, I hope I'm about to answer that question. So, but let me put this warning up first. Buyer beware. Right. So, where am I? So, as G goes to infinity, the story is less explicit. But in a sense, it's more rigid. And all the stories in all G are related, as I'll explain, sort of with some ideas that come from GT, Grothendieck-Teichmüller. So it's hard to write down integrals of things. Yeah. that you can compute here, I mean, or that I could compute. I mean, I'll make a remark. I mean, in the genus 0 case, everything is of type PP, right? And things of type PP in Hodge theory, if you've done it, are a lot easier to compute. You can write down explicit forms. If you, the minute you go to higher genus curves, it's much harder. You know, I mean, if you want an exercise, you know, things can vanish in cohomology that don't vanish as differential forms. So that's one reason why things become more complicated in higher genus. All right, so, and I wrote here issue. This is partly an answer to Don's question that I'm going to elaborate on. There's one, well, only one curve, one projective curve of genus 0, but there are many of genus positive, right? When the genus is positive, there isn't just one curve. So because of this, we have to look at the moduli space. So we've got
your point? I still don't know which G is. In the case when G is 0, I see two G equals 0, so I ask which G are you generating? G is the genus of P1 minus P1.
correct.
The G is also, that's also the multiplex curve to G, there is 4 multiplies. So when you go on and you go, are you changing the G?
Okay, I'm about to get, okay, maybe I'm going too slowly. Okay, moduli, let me just say, I think I'm about to answer your question. But if I don't, please let me know. All right, so let's take mg. Okay, I'm going to do the thing in its full glory. N plus r. So this is a notation I like. This is equal to the moduli, whatever, space. I think I want to say stack or orbifold, whatever, of smooth projective curves of genus G with n distinct marked points and r non-zero tangent vectors. So let me make a little, so let me just draw a picture of something that might be one of these guys here. You have a whole bunch of marked points, they're all distinct, and I want to add tangent vectors at a couple of points. And the points have to be different from each other and different from these, right? So there's going to be r of these. Now, we're going to have tangent vectors because like in the genus 0 case, you want to, you know, with P1, you have to take tangent vectors at 0, 1, and infinity for various reasons that have been explained. But if you're a topologist, you want to, how do you think of this? Because we sometimes want to take pi1 with a tangent vector at some missing point. What people do is you could look at the real oriented, you could take the real oriented blow up here, which means replace this point by all the rays in the tangent space at this point, and it replaces that boundary component with the circle. What have we got genus for? Right. So you replace these here, and each of those tangent vectors gives you a point on the boundary, right? And you might argue, well, what if I made it twice as long? Well, in some sense, we're only going to care about the direction. And then we've got our marked point. So this is the topologist picture, and this is the sort of picture that we care about, right? But it's a good idea to think of these guys. You can take the blow up because we may want to glue these guys together. That's right. So for example, I'm going to want, I want M1, yeah, so the points in this correspond to complex structures on that. And it is, in fact, in some formal sense defined over Z, but I mean, we can talk about it over anything. We'll often, when we're doing Hodge theory, we'll think of this as some complex manifold. When we're other situations you want to do, a tile theory, you need to take it to over Q or something like this. So M11 would be equal to these guys here. I'll just give you an example. Elliptic curves with a non-zero tangent vector, but I claim this is just C2 minus the discriminant locus, and I wrote it down somewhere. Let's see if I get it right. 4a cubed minus 27b squared. And AB here will correspond to the elliptic curve y squared equals x cubed minus ax minus b. This is the condition that it be smooth as the discriminant doesn't vanish. And then what about the tangent vector? Well, if you write down something in here, you get a differential dx over y. That's an abelian differential. And because you've chosen the coordinates, this is fixed. And then the tangent vector v is the unique one on which this differential takes the value 1, right? So this is a nice concrete thing. And while I'm here, a little bit of culture. I mean, so what pi 1 here of M11 is isomorphic to the braid group on 3 strings. It's also a central extension of SL2Z by Z. All right, so that's an example. So this would be the analytic guy, but you can do, I mean, I didn't write, you have to be much more careful about how you write down this equation if you want to do it over Z. I think this works away from the primes 2 and 3, is that right? I think so. So, right, and now what we have is so I hope I'm answering Don's question here. I mean, there's no preferred curve. So I'll take something like mg, say 1. So for example, I can take this here, and now I have a section, so I have a base point. So there'll be this is curves plus 1 point. This is the universal curve. And again, I'll just generally simplify to this, and then this is the tautological point. There's everything down here. I mean, you have a point in here corresponds to an isomorphism class, a curve plus this. Over at the fiber is C, and the section just takes this guy up to the point X. And you can write down this as a quotient of some contractible space by a mapping class group. Probably get to that later. Sorry?
You're now talking about MGN is which I know, but my question was, is this P1 in your generalization? This is two things. It's the curve classified by M03.
Okay, let me look at my notes.
It's the one space M04. And I'm just
okay, so what
is it
I want to, okay, so I think the answer, so it's about, let me write down one more thing here. Okay, X over AG is the universal abelian variety. Right? And now, example, and I'm going to do, I mean, you can take M0n, but here I want to take what's M03. It's just one genus 0 curve with 3 points, and this is going to be spec Z. And then over it, what's the universal curve? That's going to be P1 over Z. This is the way I'm looking at it. And then you've got three tautological sections here. They become, the 3 tautological sections are 0, 1, and infinity. Right? So you have these guys contained in here. These are the 3 tautological sections. And so, in general, I want to think of the universal curve over MGN. There's no one preferred curve, and I think with elliptic curves, there's no elliptic curve over Z, which has everywhere good reduction. If we want to work over Z, we want something to have good reduction everywhere. So we want to, the moduli space does have. Okay, so what, I think there was another question. What was the replace, okay. and I'll just make this remark now, I won't write it down, is every one of these guys has good reduction at every prime. So it's smooth over FP, which is something you want if you want motives over Z and not over Z with some primes removed. Okay, skip all that. Okay, maybe I'll come back to that. Okay, so again, G equals 0, we have certain things that we know. We have Q of n, right? So what are we going to replace these guys with? This is G equals 0. So G bigger than 0, what do we want? So we have the curve here over, I'll just write mg, and this means any decoration you like. Okay, so this is the universal curve. So we have a local system over this whose fiber over, say, C with whatever decorations we specify. Sorry, this is over mg star. And if this is F, a fancy name for it is R1 F lower star of Q is a fancy name. But in concrete language, what is, and I think I want to make it have weight 1. So weight minus 1, sorry. Just for those who like weights, this is weight minus 1. But what is this? The fiber, if you take C with whatever decorations in here, the fiber over this is just going to be H lower 1 of C with Q coefficients, or whatever coefficients make sense. So L-adic coefficients if you're doing Galois theory, right? So the fiber of this local system over a point is just the abelianized pi 1. And now, right, and so what other local systems do we have? I should say something, what's the monodromy? So there's a pi 1 of the base, so let's just say, over the complex numbers, pi 1, if we look at it as an orbifold, say pi 1 of mg, say n, is equal to the mapping class group gamma gn. And this is by definition pi 0 of the orientation preserving diffeomorphisms of our reference surface that pointwise fixes the end point. So this is a genus G reference surface, and we take the group of connected components, and this group maps into the automorphisms of the homology of the surface, the compact surface, preserving the intersection product, and this group is also known as the integral symplectic group. And it's well known that this is surjective. Right? So, and what representation is this? It's just this tautological representation here I'll call rho. So the monodromy is just rho takes pi 1 of mgn into SP, I'll call it SPH. Right? And it's Zariski dense, the important thing. And I'm going to put here with Q, and this is Zariski dense. So this is an algebraic group, and that tells us we get local systems by looking at all irreducible representations of the symplectic group. With the eraser. So So if V lambda, say, is an irreducible representation of SPH, and so these, by the way, these correspond to partitions. So partitions have come up in several other talks. You just look at partitions of any integer into no more than G parts. And these, right, so this Young diagram or Ferris diagram will tell you what it is. So every one of these gives you a representation. And for example, if I just look at n boxes in a row, this corresponds to Sn of h. And if I look at, say, k in a column here, this corresponds to, you might like it to correspond to this, but this is not irreducible. You have to take the intersection pairing and mod it. I mean, the exterior algebra is an algebra, and you just mod out by the ideal generated by the theta divisor, by the class of the intersection pairing. And here, k of k is less than or equal to g in this case. Right? That's an example. So each of these here gives you a local system over mgn. And it's actually, I didn't mention, this guy is a nice motivic, this is a motivic local system. And to me, I'm an old-fashioned guy. That means compatible realizations. So it's a polarized variation of Hodge structure. So I don't want to, I know from experience it's not a good idea to drill too deep here. Just a natural local system that occurs in Hodge theory, and this is the Hodge version, and it's a Lease sheaf in the L-adic, Lease L-adic. If you tense it with QL, and if you take the base field to be Q, right? And there are more things that's probably, I'm sure it's crystalline and all of these things. But, all right, so you've got this guy, and you can also twist it. So you can also take V lambda R is just equal to V lambda tensored with Q of R. We know what Q of R is. It's the Hodge structure, for example, of type minus R in Hodge land, or it's given by the cyclotomic character, the rth power of the cyclotomic character in Galois land. So I can take this, and these are all motivic local systems. So this is just, this is motivic in the same sense as above. It's a polarized variation of Hodge structure and so on. So these are going to be our basic pure objects. So we've got a lot more. So example, if you take genus 1, what you get is the sort of basically the simple local systems are going to be, you'll get all the, well, you get Sn of h r, right, where n is greater than or equal to 0 and r is in z. And that includes all just the QRs. And that's all you get, because in G equals 1, you just get this first row, right? And the representation theory of SL2 is just these guys. Actually, when you put the twist in there, you're really looking at representations of GL2 in this case and GSP up there. But I won't go too far that way. All right, so what we want to do is so what do we do we want to look at interesting extensions of these that are defined over the moduli space and extensions. And so the idea is in G equals 0, what we wanted to do is we wanted to understand mixed Tate motives over Z, and these were basically extensions of Q by Qn, et cetera, extensions in here. So let's take, and I guess the point of Deline's paper was, where do you look for these? You look for these in pi1 unipotent of p1 minus 0, 1, and infinity. And you have to take an appropriate base point. The base point V is just ddx. It has to be an integrally defined base point. But now let's look at G bigger than 0. So where are we looking here? We want to take, we've got the universal curve. So again, I'm probably still answering Don's question. Let me take mg1. So here I'll take G greater than or equal to 2. I've got my tautological section here I'll call XO. And now I could look at some bundle, and I'll call it P for want of a better name, over mg1. This is a local system. And over the point CX, what's the fiber going to be? There are various things you could take, but let's take the Lie algebra of pi1 unipotent of Cx. Right, so these guys form a local system, and all the graded quotients are local systems of this form. Right? So this is a local system, and it has a weight filtration. The weight filtration is nothing other than the lower central series. The weight filtration is W minus N is just the right. So it's just the weight filtration is really just the and every graded weight, say -1 of this, is just equal to the local system H, and the graded weight minus whatever minus M is just going to be some sum of V lambda I Ri, right? By the way, I should say the weight of this guy here, the weight of this is the number of things in lambda minus 2r. This thing here lowers the weight by 2, and so we have this guy. So to answer Don's question, we're going to say we're replacing P1 minus, say, 0, 1, and infinity over spec Z, which is just M03. This is M04 as well. We're replacing this by the universal curve over M, say, G1. You can add more points, but let's just look at this. Right, and here we're replacing the unipotent fundamental group of this by this entire local system here. And so we're replacing, maybe I can,
if you add more points.
Sorry?
If you add more points, then the filtration won't be local.
Yeah, but it changes it. I mean, I don't want to go there, but it's well understood since 30 years what happens. And it's nothing, if you remove 1 point, the lower central series is still the weight filtration. If you remove more, the new generators in homology have weight minus 2, and you just take the sort of so-called convolution to get. Right, and so here, pi1 unipotent of P1 minus 0, 1, and infinity, this gets replaced by P. Right? And, you can think of this P, it's really the representation of pi1 of the base of one particular fiber. So maybe I'll say more about the elliptic case. So let's just say a little bit about the elliptic case. So I'm going to, okay, first of all, we have E as an elliptic curve. It's not hyperbolic. Right, so it's got a boring fundamental group. So there's nothing interesting in there. Now we'll take E prime in this case. It's going to be E minus the identity. We can do that. But now we need a base point, and we're faced with exactly the same problem as we are with P1. The only sensible base point you can take, if we want to take a base point to be a tangent vector at the identity. And so a base point is going to be a V element of the tangent space at the identity of E. Sorry?
Why do you need that? I mean, if you just remove the point, it would be hyperbolic. You don't need
Right, but we want to look at pi1, and you don't have pi1 without a base point.
That's it.
Right, and if you say, well, it doesn't matter which I choose, well, when you go around here, you end up going to generate the loop around this point, and when you mod that out, you've just got pi1 of the original curve back again. So, what I'm just trying to say is the moduli space we should look at is M11, which is the one I was describing before, which is C2 or A2 minus the discriminant locus. And you've got the universal elliptic curve.
Is this playing a role of killing the
stackiness of the base, or that's not?
Well, that's not a reason for doing it, but it does.
Okay. It does, but that's not the reason. Okay.
Right.
Yeah.
I mean, yes, so this is a genuine scheme or whatever. And so then we'll get E, and we remove the 0 section, you get E prime. And now, and you have a tangential section, this tautological thing. And to make this even clearer, I mean, here's another way of drawing this. Here's the base. We've got the 0 section. And now what's the normal bundle of the 0 section? It's, well, what's the tangent space at the identity here? It's the holomorphic differentials. So this is just the relative holomorphic differentials, which is exactly the line bundle you use to define modular forms. Right? I mean, so okay, and so now we're going to have a bundle. So P here will be a bundle over, you know, M1, 1. And if you looked at the point corresponding to EV, the fiber over this is going to be pi 1 unipotent, or the Lie algebra of that. By the way, in this list of names here, I left out somebody, Levin Rassanet. Sort of. So you would take E prime V. And when you want to take pi 1 with, say, tangent thing here, you should really blow up that point. I mean, and just say, well, this tangent vector determines a point in this, and just take pi 1 of that. That's equivalent to the standard definition of. All right, and what is this guy here? Do I have colors? This guy here is just a Freely algebra on this guy here is isomorphic to, not canonically, to the Freely algebra on H1 of the curve. Right, because it's a free group of rank 2. Okay, so I want to, there's a hard part to talk about here, but in a way it's easier to, it's maybe easier with you guys because you regularize integrals and so on. But, so, G equals 0, you all have this thing. You've got 0 here, 1 here, and you know that if you take, you know, omega to be dz over z times E0 plus dz over 1 minus z E1, which you think of as taking values in omega 1, P1 minus tensored with this algebra on these two guys. And you let T be 1 plus. The nice thing is here is everybody knows what iterated integrals are and so on. And if you integrate this iterated integral, say, from epsilon to 1 minus epsilon, and then you let epsilon go to 0, you know this guy diverges. But there's a way to regularize this by basically the infinities come from polynomials in log epsilon, and just set log epsilon equal to 0. That is the same as computing a limit mixed Hodge structure on, say, pi 1 of the paths from here to here. There's some prescription due to Deline for doing this. And so higher genus, right, in higher genus what happens is, yeah, so in complex analysis there's a basic idea that growth of something depends on what happens when you go around it, right? If when you go around something, you get no monodromy, then there's no growth as you go towards the middle. So what happens here is this local system degenerates. So I'll say here, H degenerates as you go towards the boundary. of moduli. So let me, and you have to regularize. So mixed Hodge structures have periods. In the genus 0 case, the periods are just the coefficients of the monomials in these guys here, and when you take regularize, they become multi-zetas. So likewise, you do this in higher genus. You've got to, and we want to look at how the periods behave when we go towards an arithmetic base point, and I'll explain that in a minute, but let me just do this here. Example. Let's take g equals 1, and I'm going to take the local system H over M11, and if you like, this contains the Q disk. Right? So Q being e to the 2 pi I tau, and you get, right, so you've got the universal elliptic curve here, you can restrict it here, and what's the central fiber? The central fiber is a nodal cubic that looks like this. So what's a nodal cubic? This is really equal to P1 with 0 and infinity identified if you choose coordinates correctly. And then you've also got the identity down here. And so if you remove this, well, okay, let's draw a topologist picture here. You've taken, so P1 has 6 natural integrally defined tangent vectors. There they are, right? Because these are tangent vectors that are non-zero at every prime. And so you should think of this thing, if you want to deform it, to deform a node, you have to take a tensor product of a tangent vector here with a tangent vector here. And what does that amount to? It's the deformation, the first order deformation corresponding. So here, the fact that we want things to be integral and non-zero at every prime says we can only choose 2 tangent vectors on each branch here. So there's only 2 ways to glue this. You have to glue it this way or that way. And they correspond to deforming this guy here. Here's the Q disk. There's 2 tangent vectors here that are integral and have everywhere good reduction, and minus ddq. And they're exactly the guys you obtain by taking this and gluing the 2 different ways, right? And so this is basically the Tate curve. And we want to take this to be our fiber. This is a smooth elliptic curve, sort of infinitesimally close to 0. It's the analog of choosing. And if we want more of a tangent vector here, we can also, our tangent vector here is going to be the other integral base point here. And so what happens to the periods of this H? So this is one of the confusing points to non-professionals. This H1 of an elliptic curve, which is manifestly not Tate, is a Hodge structure. It's got a 1, 0, and so on. So let me just let HT, this is going to be H1, let me call it HQ of EQ. That's the elliptic curve that's over Q. So this would be EQ here. It's a nice smooth elliptic curve. This degenerates to, well, I don't want to go all the way to E0. I want to go almost all the way to E0. I want to go out here, and it's H1 of this guy here, and to H1 of E, I'll call it ddq. And I claim this is just Q direct sum as it's actually it degenerates. So you think this is weird. This guy has weight -1, and this has weight 0 and -2. But this is how this theory of limit mixed Hodge structures works, right? So the weight -2 guy is the guy that circles here, and the weight 1 guy is the guy that's sort of determined by passing through the double point. Okay. And so what happens here, what do I want to say here? So one way we say this is H is an admissible variation of Hodge. Sorry, it's a. Actually, I want to say, or a polarized variation of Hodge. It has this nice limit behavior. The periods behave well, and when you calculate the degeneration of, you get this guy here. So higher genus is similar. How am I doing here? Not. I've got about another 30 minutes to go. Similar. The sort of base points you want to use are Mumford curves. You replace, I should say there's also a Natal analog here, so you can also do this in Natal land. Mumford curves. What's a Mumford curve? Let me just give you an example of genus 3. It's a maximally degenerate curve. So how do you get a degenerate stable curve? You choose a whole bunch of simple closed curves on it. A maximal set of non-separate, something like, it's called a pants decomposition. We divide the surface into pants here. And if you contract all of those, what do you get? You get a whole bunch of copies of P1 with 3 points on it. And if you put little pairs of points everywhere, you can see that you've got, you've got a first order deformation of such a thing. And that's going to be the analog of the first order Tate curve. So this thing I'll call CV. I don't know if this makes sense or not. So it's a first order smooth. You would get a nodal curve by collapsing all those curves. And you can get an integral. So it's defined over Z. So these guys are defined over Z. And these are sort of tangent vectors. Of MGN, they're tangent vectors at infinity that play the role of the 6 natural tangent vectors in genus 0. All right. So, and now there's a theorem here. It says that if you look at pi 1, so this is with Matsumoto. If you look at pi 1 unipotent of a Mumford curve, and you look at, say, the Lie algebra of that, this is actually a mixed Tate motive in spec C. As you might imagine, just gluing together a whole lot of P1 minus 0 ones and infinities using only. Okay. So a corollary of this is all limits of this local system, P over mg with whatever decorations we choose here at Mumford curves. You look at the universal curve over this. I mean, there are punctured versions of this and so on. So now I want to say what local systems we're looking at. So G equals 0, you have MTMZ. G bigger than 0, I want to look at a category that replaces this guy here that we want to understand. And so what is it? This guy here is going to be, it's going to be the category of, so I'll give you, say, this is the Hodge version. It's the category of local systems over mg with whatever decoration you want that you need. So, for example, mg1 or e1 vector 1. I'm going to say admissible variations of mixed Hodge structure. So admissible variations of mixed Hodge structure are variations of mixed Hodge structure that have very strong good limit properties, which hold here. such that the limit at each Mumford curve are in M, T, and Z, and whose weight-graded quotients are sums of things like V, lambda I, Ri. So they're successive extensions of these guys. And the point is, maybe this category is empty. So this is the Hodge description of these guys. Is this category empty? And for example, this fundamental group torsor is an element of this category. So that's what that theorem over there says. So you have this nice thing. So it these maximally, I should also say that this point, this guy here, if you think of it as a curve here, is an element of, it's a tangent vector at infinity. In this case of mg.
So here you're thinking of categories of systems, compatible systems of realizations, right?
Right. Like I said, I'm an old-fashioned guy, so I think of compatible realizations. No, but I think it's a year since I looked at this. When you prove this theorem, we can actually prove this guy's a mixed-state motive, because you can write down it's the coordinate ring of the Lie algebra, its unipotent thing in terms of paths on P1. So this is actually true, right? So now what I'd want to say here is that you have this variation of mixed Hodge structure, you have the étale local system, and when you look at the limits in both cases, they're the realizations of an object of mixed-state motives over Z. Is that?
Yeah, I'm not sure whether that proves that it actually comes from an object.
Okay.
But it doesn't matter.
All right, so okay, so this is a proposal. Okay, so I'm almost out of time. So let me try to say something. I mean, so all of this is just explanation or language and so on. But I mean, what can one do? So I'll just try to give a very quick summary. I mean, I find this stuff very hard to explain to a general audience because, different people understand different things. But I mean, sort of, what can we do? And I'd like to call this category the category of universal, say, Teichmüller in general, and universal because they're defined for the universal curve, and in the elliptic case, they'll be elliptic, mixed type. Mixed elliptic motives. So there'll be universal elliptic motives. And so they make sense for all elliptic curves in some sense. So what can we do? Well, one is these categories are Tannakian. And so they're the representations of some pro-algebraic group. And so modulo some conjectures in number theory, and I can be more explicit, but it's basically about H1 with coefficients in things that come, the representations that come from cusp forms, because nobody knows how big this is, but there's a conjecture as to how big it is. We can mainly compute, I'll put it like this way. It's the Lie algebra of this group, so this of pi 1 of, say, mixed elliptic motives, the genus 1 case. And the point is, it's going to be an extension GL2, so it's an extension of GL2. There's some group here, and there's a unipotent radical. And this unipotent radical here, so this is pro-unipotent. And there's two kinds of generators. There's all these guys, Z3, Z5, and so on, coming from mixed Tate motives. And in addition, you get a whole bunch of E2n plus 2 here, n greater than or equal to 0, where this corresponds to G2n plus 2, the Eisenstein series. But the unipotent radical is not free, and there's two kinds of relations. One that tells you, so the part generated by these Eisenstein series, I should say each of these has a copy of S2n. The generators, these all correspond to the trivial representation, and you'll have these guys here. There's two kinds of relations, and they come from, one comes from knowing how, actually we don't know these relations at all, we just know they're there, say how the Z acts on the E's, and this will be in the ideal generated by these guys. And the other one, so these are sort of the infinitesimal Galois action. The other part is how relations between, sorry for doing this, the E's, and it turns out that the basic ones of these, they come from these guys here. And modulo these relations, so up to the Galois action, these guys, for each Hecker eigen cusp form, you get a quadratic, cubic, quartic, and so on higher relation among the E's. And we believe they're all non-trivial. There's still more stuff to be done here. And like I said, I haven't done much on this in the last couple of years for various reasons. So in some sense, this is pretty well understood. So we have a pretty good idea of this. And Aaron Pollock's going to talk about these quadratic relations, and maybe even Francis as well. In higher genus, what happens, this unipotent radical has got an infinite number of geometric generators. Before I mention rigidity, sorry, my hour's up. The number of these extra generators goes down to just one or two from a countable number. And this is the rigidity. I mean, we know enough about, and we also know about relations in higher genus. All the stuff, all the cohomological calculations come via geometric topology. So we know a lot there. Genus 2 is a mystery. Genus 2, I think it's computable, I just don't know. I mean, there's some questions in either geometric topology or something that I don't know how to solve. Genus 3 and higher is simpler. But all that said, everything is really coming from genus 0 and 1, because in the moduli space of curves, you can compactify it with this Deligne-Mumford compactification. These Mumford curves are the zero-dimensional strata in this compactification. Their one-dimensional strata are coming from M04s, which is just P1 minus 0 and in infinity, and also M11s, which is the elliptic case. And you can prove that the mapping class group is generated by a neighborhood of the sort of two skeleton of the boundary, the two-dimensional strata M05 and M12, and that's all there is. So this makes it fit in with, Grothendieck-Teichmüller theory. So there should be, I mean, all this stuff should fit together in some way that I don't understand. Yeah, I'll stop here.
Questions?
So in the hyperelliptic case, do you expect that to be a lot, or do you have any
Well,
idea?
I used to think, and then I hadn't thought. Okay, so mapping class group of higher genus is an extent. Let's just do no points, right? So you got this maps into mapping class group into STGZ into 1. So the first, and I should say in the case of abelian varieties, if you just take the universal abelian variety or remove its zero section, you get nothing very interesting. The first thing is this group becomes rigid once the genus is 2, which means it has no H1, and you don't get any 1 extensions. So if I looked at these local systems over G, AG, or xg, there's just nothing. Everything splits as the sum of the v lambdas in both Hodge and Attal lands. To get anything interesting, you have to remove the theta divisor. You have to create pi 1. The only way and so you can think of the elliptic case, where you puncture the elliptic curves. You take an elliptic curve and you remove the odd theta locus, because that's what the identity is. It's the 0 locus of the odd. So here you could take either, to get something defined over z, I presume you have to take all even or all odd theta divisors and remove those. And then you create pi 1, but there's still not a lot of cohomology here, so there are very few extensions. So in this case here, how do you compute extensions? This group's rigid. Everything's coming from the Torelli group. So this is why a nice topologist like me is sort of hanging around doing stuff like this, because I understand the cohomology of this group. There's no Torelli group in genus 1, but SL2 is not rigid, and that's why you get all these modular forms. And so in genus greater than or equal to 3, H1 of T3, say T31, let me put N here. This is just the third exterior power of H. That's all you get. And this is the only thing representations contained in this can have. You only get extensions from this. But this is for G greater than, this is G greater than or equal to 3. But in genus 2, you get that H1 of T2, let me just do T2. It's some big induced representation from S2 semi-direct product SL2Z squared up to SP2Z of the trivial representation. And now you say, what are all the algebraic quotients of this? So this is not an algebraic representation. And if you work that out, it's the sum of all spherical representations of this. So you get all the guys that have an equal number of things in both rows. So they're the highest weight part of symmetric powers of S n lambda to H in this case. This is all you get. So there's a huge amount. So potentially all of these guys have non-trivial H1. But you still have to have a differential from H1 of these guys into H2 of the symplectic group with these coefficients. And I only know that differential is non-zero for two of these representations, this guy and this guy. And I know how to sort of motivically, these guys occur in pi 1. That's how I know they're there. But potentially all these guys occur, and so you'd have an infinite number of 1 extensions. But they may not, because maybe H2 of the symplectic group with coefficients in these guys is non-zero. I don't know.
In your title, you had the word polylogarithms.
Yeah.
All right, let me do polylogarithm in 1 minute. Is you would take the universal curve over mg1. You've got a base point section, and now you look at the relative path torso. I just took with relative pi 1.
For layman, in these terms, could you pin down a function that plays the role of the usual?
No, but, well, two things. Maybe you guys are really good at this. But the minute you get up here, what are you working on? You'd be writing down functions on Teichmüller space. I mean, there are lots of things that are hard. In genus 0, this connection is trivial to write down. dz over z times something plus dz. In higher genus, even for a curve, there's no canonical way to do it.
Genus 1.
Sorry?
Genus 1 Teichmüller space is pretty explicit.
Yeah, no, you can, this is what Lev and Rassenet, for example, did, and it's all the Durham thing you can't write down all these other local systems. Maybe you can write down.
A local system, he's asking for a function of a complex variable.
Sorry?
He's not asking for a local system, but a function of a complex variable. Same in genus.
Okay, but in genus 1, Lev and Rassenet, and also I think this is Kalak and Requez, Eddinghoff or something. There are all sorts of complicated formulas that you guys may love. I mean, big things with lots of theta functions and so on in the Eddinghoff and company one. And in the other one, they use stuff, Eisenstein series and so on, to write down these connections. So you could look at this stuff and try to compute. I mean, but part of the problem is, you have to compute it on all of the upper half plane cross C. and there'll be some big iterated integrals you can write down, but maybe you can do those integrals.
Wouldn't you expect some sort of vector value functions anyway, because you're going to be looking at different representations of the symplectic group and taking values on this Teichmüller space in these, precisely in these representations.
Yeah, I mean, yeah, okay, so that's another thing. You've got to pick off the periods. So yes, things are going to land in some space of periods, and I have to think about what.
Can I give a very short answer? One way a naive way to do it is to take multiple polylogs and average with respect to the Q. You get garbage if you do that, but if
Yeah, read
you do it a bit more subtly, then you get something totally different.
Or elliptica.
Only in the case of elliptic.
Yeah.
And
Maybe it's irrelevant. It's about the word motivic, and how can you deem the things motivic for, say, G larger than 3?
So how can I say that they are?
Yeah, that they are motivic for G larger than 3 when MG itself is not really a motive for G larger than 3. So
Okay.
you have, let's say you have local systems over something which is not which we don't know is a motive, and then how can you say that the monodromy is motivic?
Okay, so let me. Yeah, that's a good question. So part of this is sort of inspiration. I said I'm a compatible realizations kind of guy. But the other thing is, I believe, I can't, I don't know if we can prove this or not. I can't remember. But so I said that this category is the Tannakian category. You can say, what's the Hopf algebra that occurs? So it's certainly true at the level of realizations that O of pi 1 of, say, mixed elliptic, these universal mixed elliptic motives is a Hopf algebra in mixtate, in the category of mixtate motives over Z, at least on the level of realizations. But I think we convinced ourselves that this was actually true. And I haven't thought through the whole higher genus thing. There are some tricky questions. Yeah. But if you looked at mixed Teichmüller, oh, that's bad, right? You know, after the fact, and which fiber functor we're using? We're using the fiber functor at a Mumford curve.
Yeah, sure.
Right? So if you use fiber functor at the Tate curve here, you get, I believe, don't quote me on this, I mean, certainly at the level of realizations, you get a Hopf algebra in here. So I think what I would expect to happen for all G and N and everything, as general as you like, the coordinate ring of the Tannakian fundamental group is an object in this, and that makes it motivic. If that's the case. And if it's not, I'll conjecture that that's the case. Yeah.
Can I ask a question? So we know that MTMZ is obtained by taking Q and QN and taking extensions, right? So are there similar objects for MEM?
For MEM? Yeah, these just Tate twists of symmetric powers of, in genus 1, just Tate twists of symmetric powers of the fundamental representation of SL2. Or if you like, just their representations of GL2. And in higher genus, it's just Tate twist of the irreducible representation of SP, the same as representations of GSP. So they're the simple objects, and now you want to understand extensions. And we know enough, except in genus 2, we know all the cohomology to tell us all the X1s. And the X1s in genus 1 are connected with modular forms.
More questions?